Okay, if you can't find the class webpage, you can just go to my webpage. Google Remzi. Remzi's haven't taken over the world, so I still show up somewhere there. There's a rather old picture of me. I look so much younger; it's frightening to me. Anyway, there's a link off there if you can't find it. Um, and figure that out. So that's the web page. This I'll shrink, and now we're going to go to lecture mode. So now this is the first real challenge of this class, which is you've been here a long time, and now we're going to do technical stuff that is detailed. This is going to happen roughly 14 times this semester, where we will have the last hour isn't just like you'd really like it to be that I'm like, and now we watch the fun video about operating systems. That unfortunately doesn't exist. And if it did, you'd feel ripped off anyway that I was just showing videos, right? That's like what your high school teacher did when they didn't feel like teaching. They're like, let's watch a film strip, or you probably don't even know what a film strip is, but let's watch something on a, whatever, DVD. We can't do that in here very often. So in any case, we're going to have to focus because we're going to get into some technical material. And some of it, when people don't like it, what they say is it's really detailed. But it is learning how things work, especially computer systems, is about the details. Like understanding the details is important. It's easy to understand things vaguely at a high level. That's called not understanding them. So don't do that. Try to understand the details because that's what learning is. It's learning all the things all the way down. And like I said, the beauty of computer science is that you can understand essentially all the details. It's just stuff people made, right? It's not like some unknowable. Like I remember I was talking to a brain scientist on campus, and I was interested in the brain and asking about, hey, you think it works that way, but are you sure? And they're like, no, it's complicated. It's the brain. It's nature. No one has the answers. And I'm like, your field stinks. We have all the answers, more or less. Not all the answers, but a lot of answers. And anyway, but they study the brain, which is pretty cool. So I guess they have that over us. Though if you've ever seen how brain science works, it's a kind of a grim field. Like, it's like drilling into rat brains and stuff like that to get like two probes in there. So that is a very fascinating but grim business. I kind of asked the guy about that too. And he's like, I'm like, how do you decide like, what's okay for you? And he said, everybody has their own line where they won't do that next thing because it's just too much. But good for them. They're understanding the brain. We'd have simpler world, right? Computers. We can poke the transistors and not feel any ethical guilt at all. So there's a sidebar that I wish wasn't being recorded. Anyway, in any case, let's start talking. And what we're going to talk about is that first part of the course, which is this beautiful, most fundamental abstraction that the OS is providing to you, which is that of virtualization. It is taking a one or few physical resources, let's call it one, but it could be, you have some amount of memory. You don't have one memory, but you have one physical memory. You have maybe more than one CPU. You have maybe 8 or 4. But let's think of it as we're taking one physical thing and turning it into many virtual ones. These abstractions are so fundamental. A running program uses a CPU and memory effortlessly, right? You don't think about how many times instructions are being fetched or data is being accessed because it's just so much a part of what is computing. But fundamentally, these abstractions are what the OS provides as a starting point to doing anything interesting in the world. It's using the CPU and using memory, accessing memory. So we're going to talk about really 2 pieces of that. We're going to talk about virtualizing the CPU, which is going to be our first focus. And then later we're going to talk about virtualizing memory. I think you've had some elements of both of those things in 354. So maybe what's nice about the class is there's a little bit of review at the beginning where we refresh on those things and then hopefully get a little deeper into it before we get into the other topics in the class. So let's talk about this virtualization. Let's do it on a new page here. And like I said, I'll be sharing this video to the extent that I remember taping it, which I am doing now. And then also this Notability app. Again, I have no stock or money invested in Notability.com or whatever this company is. It's this $10 app, and it produces a beautiful PDF at the end. So I'll share that PDF of my notes. That said, if you're wondering like how to get something out of lecture, it's not a bad idea to take some kind of notes or do something that forces you to kind of go along with the class as opposed to just realizing that this will be available to you. First of all, because I might mess up and not, be able to upload everything properly. And second, just to keep yourself engaged in what's going on in the class. So anyway, we're talking about virtualization. Um, we think of this as really, it's an illusion, right? It's this amazing thing that the system is kind of lying to you. The system is creating this world where you think, each running program thinks it has its own CPU, and it thinks it has its own private memory. These are not, to the extent, it's kind of true. It looks like that. It's true except for timing. Like if many programs are sharing the CPU, you run more slowly than if you're not, generally. But it's generally like that's the illusion that's being provided by the operating system, and it's a fundamental thing. And we'll talk about how cool that is and how to realize that. Now, there's a few pieces we want to think about how to do this, or a few key aspects of virtualization. One is that, like we talked about, when we're providing OS features or OS abstractions, we're always going to be concerned about efficiency. It would be no great thing if I said, hey, I built this virtualization of the CPU, but it runs 20 times more slowly than if you just used the machine, the raw machine. There is some overhead we're going to pay, and we'll talk about what those overheads are and why they're there. But the overheads have to be as low as possible so that we're not wasting computer time doing just this kind of virtualization. And then the other, of course, aspect, which we also talked about, is this kind of security aspect, which is that we're going to be, when we're running user programs, we're going to be restricting them in some ways. We don't allow user programs to do whatever they want. If they do, they can take over a machine and they can then do things that we don't generally want user programs to do. For example, we don't want a user program to be able to read the entire hard drive beginning to end. Because it might be that there's your data on it, there's my data, there's somebody else's data, and we might want to restrict them to only access their data. We might want to restrict the program to only access its address space, its data structures, not someone else's data structures. In fact, the reason that those security bugs in Intel processors made the news is because through this very cool timing-based covert channel, it was allowing a process to arbitrarily read essentially all of memory. That's a big security hole when we build operating systems, and it turns out when we build hardware, we have to be thinking about that in a very fundamental way so as to prevent that. So we're going to think about both efficiency and kind of protection as a fundamental thing when we're building these virtualizations. Okay, so let's start talking about then CPU virtualization and what that means. So we're going to talk about taking one, or a few CPUs. I'll think of it as one, just as simpler to think of it that way, and turning it into many virtual CPUs or vCPUs. And again, that physical to virtual is something I'll often talk about here. The way we're going to do that is something called time sharing. It's a basic kind of principled approach, a basic principle behind this approach, which is when we want to share a CPU, what we're going to do is we're going to give one running program the CPU for a little bit of time. Then we're going to give the next program a little bit of time, and then back to the first one, and then maybe to a third one. That's called time sharing, and it's kind of an obvious technique that you would invent if somebody told you to invent a way to share CPUs. So that means we run program A for a little bit, then we somehow figure out how to transition to B, then to C, then maybe we go back to A, and so forth. Another natural way to share a resource, the operating system in general is considered the manager of resources, so it manages the CPU, it manages the memory. We'll talk about that as the class goes on, is to space share them. So if we take memory, it's pretty natural to split it up and say, you get this part of memory, this other program gets this part of memory. That's called space sharing. And time sharing is different. It's kind of flipping the resource between different entities repeatedly, maybe at some granularity of time. We'll talk about both of those things as we get into it. But as we think about, it's kind of more natural to think when we're sharing just one CPU, what you need to do is time share it because you only have one. And if you have a few CPUs, of course, you could divide them among processes, and that would be a form of space sharing. So in any case, that's kind of a basic idea. And sometimes people call this, just so you know, it's also called multi-programming. And that goes back to the very earliest computer systems. Like the first systems people were using, they realized it was useful to share, switch between things for efficiency reasons, as was brought up earlier. That's multi-programming. Okay, so now what we're going to do is we're going to talk about the basic abstraction of a virtualized CPU, and then we're going to get into the mechanisms of how we realize that. So the abstraction is such a fundamental thing, it's kind of hard to even talk about. But the abstraction is something we're going to call a process. This is an old operating systems term. It goes back to the very first papers, research papers on operating systems, where people say, we need a term for this thing of a running program. Let's call it a process. So that's really all it is. It's a running program. So, and the important thing to realize is there's a difference between like some lifeless bytes on your disk, right? Like when you run the compiler, like we did in the demo earlier, I typed GCC and I made a program called CPU, to show the CPU example. The CPU program is there's just some bits on a disk somewhere that has instructions in it and maybe some data. But when we bring it to life and we execute it, and we have a runtime stack, and then we have a heap, and we have, of course, like a program counter inside of it telling us where we are, that's a running program, and that's what we're going to call a process. So a program is just this lifeless binary executable. Then we transform it through the operating system, turns it into a running program. We call that a process. Okay, and maybe you know that already. So let's talk about what are the components of what's inside of a process, of a process. So I'll often draw like a process. I'll say here's a process P, for example. And we'll talk about all the things that a process can affect. So one big part of a process is the process's memory, which again is private. Remember, each running program, each process, is going to have its own private memory. And I just think, if I'm one process, I just think that's all the memory in the system. I don't know there's other memory in the system. This just looks to me like it's my memory. And we call this something, we call this an address space. And as we get into virtualization, we'll say it's a virtual address space. And we'll talk much more about memory virtualization soon enough, but for now we just know that this exists. And we've already talked about what's in here, but what's inside of our address space? What's in there? What's in our memory of a running program? Yeah. Yeah, so we have code is one thing, sure. What else? Yeah. Yeah, stack in the heap, right? And there are a few other things. There might be some like statically initialized variables or static variables that weren't initialized. Those are all part of the program too that aren't in the stack and the heap, but that's about it, right? Code, heap, stack, that's kind of what a running program is from the perspective of memory. Hopefully that's a review. But that's not all that's part of a process, this process P here. What else is part of it? Well, a key part because the memory part's about virtualizing memory. A key part for virtualizing the CPU is something else in the system that changes when the program's running all the time. What else is a program changing other than memory when it's running? One answer, nothing, but then kind of a bad question. And can't you tell when I want you to answer not nothing? Yes, you can. But I'm like, is there an answer here? Yes. Yeah. Unfortunately, I don't do that during the exams. So what else is being changed constantly? Yeah. Yeah, registers, right? So there is the register state, registers, if I can write that. Hopefully you can read that. Oh, I wrote that terribly. Let's do that again. Okay. Registers. Sorry, like I said, I usually use a chalkboard and I like walking around and it's much more lively, but then I get covered with chalk and there's no record of the class. So here we are, we have registers. Clearly registers are changing all the time. What are some important registers? Yeah, okay. Why is that one the most important? What's that has return values in x86? That's true. But what's changing? Like EAX doesn't change every instruction. It does sometimes, yeah. Program counter, right? That's a huge one. In x86, it's called EIP in the 32 bits or RIP in 64-bit. But yeah, sure, we call it a program counter, PC generically. Program counter is changing every instruction, right? I mean, it's going here, it's going here, it's here. So you take a jump, you go back over here. You do a call, you go over here. You should have a good sense of what the program counter is doing, how it's constantly changing. And clearly, that's a critical part of a running program. If you change the program counter arbitrarily when a program is running, what's going to happen? Well, nothing good, right? I mean, it's going to crash, it's not going to work, it's going to be bad, you're going to cry. Bad things happen if the program counter changed arbitrarily. Related to that, and I don't guess I'm kind of keep constraining myself with these boxes, there's circles here, there is a stack pointer, which tells us, for example, where we are in the stack. Like, oh, here's the top of the stack right now. That's what the latest stack frame is. And there might also be in 32-bit x86 like a base pointer, which tells you something else. But let's just talk about the stack pointer. It's fine. So SP is a stack pointer. In fact, I'll write these things over here so that later in your notes you won't be like, oh, PC, I know that's something. But let's just go ahead and write them out. They're important. And then, of course, there are general purpose registers, which we might call GP, stack pointer, and then like EAX, basically scratch space for programs to do their computations. Now, why do we even have registers? I mean, we have memory. It's full of our data. That's the data we want to update. These registers seem to be complicating things and adding more state. Why do we have registers? Efficiency, performance, right? It's when people build hardware, they want to be able to bring stuff in that's important to the computation into the processor and compute on it very fast. How far away is memory? How slow is memory compared to register access? What's the difference? Order of magnitude. The 1x, 1.5x, 2x, 10x, 100x? Somebody guess. Yeah. Sorry? 15 to 20, maybe 50. It depends on the memory, depends on the system, maybe 100. Memory is far away. If you always had to go to memory for everything, it would be very slow. So you try to bring everything in to the processor. You cache it aggressively. If you take a hardware course, you talk a lot about caching. And registers are an explicit form of caching, where the program itself says, bring this value in and then work on it. So, of course, those are important it's really fundamental to how modern programs work. So, yes, register state is a huge thing. And we're going to talk a lot about, this is really when we're talking about virtualizing the CPU, what we're really going to be focused on is registers, the register state of the program. And we'll talk about virtual memory in a little bit. So when we're talking about virtualizing the CPU, we're talking about registers. And then there's one other part of a program that you might care about. There's like, we'll call it I/O state. You might have, like, for example, a bunch of open files and things like that. Those are relevant to the running program. Like we opened a file in that first example I showed. That's something we'll talk about as well. Okay, so that's the abstraction. A running program has its own private memory. It has its own private registers. Now remember, there's only one set of these registers, but we're going to share them among programs by switching back and forth. So we're going to have to be careful with their contents. If we change their contents, the program's not going to work in I/O state. So we're going to focus on the CPU part here. Now, there's really two elements to this that we're going to, any time that you're talking about the operating system, what you're talking about is at the low level, there are mechanisms. This kind of tells us how things work at a very fundamental level. So if you want to, for example, build a multi-program time-sharing operating system, you're going to build certain mechanisms into it for allowing you to switch from one program that's running to another one, period. You're going to need some mechanism like that. On top of those mechanisms, I guess I'll eventually write it just right here, you're going to build some policies. Those policies are things like, I was running this program for a while, but that doesn't seem fair. They've gotten so much of the CPU. Now I'm going to switch to this other program. It's just kind of like an algorithm for deciding, how to best utilize a system given these programs. So this is kind of a higher level decision that's built on top of these low-level the low-level mechanisms that the systems provide. What I want to focus on, what I've always focused on actually in this class, is we do a lot of focus on mechanism. Because mechanism, honestly, is the hard part. Understanding how things work is hard. Once someone's built a mechanism for you, like what people will call an OS scheduler that switches between processes, deciding how, like the policy that does that is relatively easy. It's just like writing a little bit of code that says, oh yeah, if this one's run for a while, switch to that one. Or if this one the user is Remzi, give that priority on the CPU. If it's just some student, kill the process. That could be a policy. You don't want that policy probably, but it's a point is it's not hard to come up with also bad policies. In fact, by the way, that was actually the reverse of that was a real policy when I was in grad school. We were working on this distributed operating system, one of these early distributed operating systems. And then I was trying to launch a program, and finally, the people that were working on that, I wasn't part of that team. I was trying to launch a program, and it kept failing. And so then I went to them, and I'm like, every time I run this, it fails. And they would run it for themselves. It works. Then we start looking at the code together, and eventually they got to a line of code which they had written and forgotten, which said, if the user is Remzi, fail. So for a while, that was I'm like, at least you could remember that you put that in the code. And they're like, well, it was a while ago, and then we forgot about it. So isn't that funny? Yeah. I'm glad we all wasted this time together. So that's an example of a bad policy. Anyway, we'll talk more, or a good policy. We'll talk more about policies later. What we're going to focus on for today is the low-level mechanisms in order to understand how to virtualize the CPU. Okay, that's going to be our main focus, and we're going to answer a few questions in doing that. Okay, so let me start talking about that. What I found when I first started teaching this class was in fact, in other OS books, there was no kind of good way to talk about these mechanisms. For some reason, people would kind of talk around it without naming it. And so finally, we just kind of named it. And this isn't a name that's used necessarily widely, but it's something that I think is a good way to think about what the core mechanism is. And so the core mechanism behind really all the CPU and memory virtualization is something that we call limited direct execution. And I'm going to give you an idea of what that is now, and then as we talk about it a little more, you'll see in more detail what I'm talking about. The direct execution part of this directly pertains to efficiency. So what that means is CPUs are very fast. Like we talked about, amazingly, they execute billions of instructions per second. It's still just unbelievable. Honestly, like I have trouble believing like that motors were at 1,000 RPM or 7,200 RPM. Like a modern disk might turn at 10,000 rotations per minute. That's really slow. Like that's why disks are going away, hard drives are going away, because they're so slow and mechanical. Computer systems, billions of operations per second, which means that CPUs are super fast, which means if you want to run a program fast, even though you're trying to provide this virtualized environment, you better run, mostly what you need to do is just run directly on the hardware, on the CPU, on the hardware. Right? Hardware is fast. So if you want to use the hardware effectively, you run on it directly. Now the problem we have is if we just let a program run on the CPU and we're not careful, is it can suddenly do anything that it wants. So if we just do direct execution, hey, I'm going to run your program, you do whatever you want, we're going to have a problem because we're going to lose control of what's going on from the perspective of the operating system. So that's where the limited comes up. This comes from the side of security or protection, is we want to set up an environment where we are running code efficiently on the CPU, but at certain key points, we want to get involved through some hardware and OS support in order to prevent the process from doing whatever it wants. We want to limit it. We're creating a kind of a cage around a sandbox, sometimes people call it a sandbox environment, where the running program can't do whatever it wants. And that's the key to how we're going to efficiently provide this virtualization and do so securely. So that's a high-level idea, and we'll talk about how that works in more detail. Any questions about that? Does that kind of make sense? Okay. Let's go ahead and start talking about it here. So to understand that a little better, let's start with a protocol that isn't limited, what we'll just call direct execution. Okay, so this is the not limited version of this. Okay, so what does that mean? And so then we're gonna show like a basic approach to running a program, And then what we're going to show is what the problems with that are, and then we're going to try to build some solutions to those problems. And then once we get through those, just 3 problems that we're going to talk about, then we'll be at the end of lecture, and we can all go home and immediately wonder, are the videos up yet? I want to see this again. That's how good it was. And feel free to show it to your friends, family. You can all sit together. I've been told a lot of people, no, that's not true. Okay, so anyway, so none of that is true. So the thing is, we're going to talk about those 3 things, but then we actually will be done, and then you can actually go do whatever. So what is direct execution? Well, it would mean this. Like, let's say we have our system, and we want to, we have an OS that's, the OS, we don't really kind of know what's in the OS yet, but let's say right now it's something simple, which is it's kind of the first program that runs on your machine. So it's running on your machine. It boots up and it runs. And we'll talk more about what happens during boot time, which is important actually, soon. But it boots up and it runs. And at some point you decide you want to run actually a user program. It turns out people don't buy systems just to run the OS, because the OS isn't really doing anything. Sadly, it's just waiting for you to help you do other things that are more interesting. So now, yes, the OS is the first program to run, but our goal is we want to, say, run some program, and let's call that program a very nice name, like A. Okay, we want to run the first program, program A. So where is A? Let's think about our computer system. Okay, I'm going to leave that there. A is, usually is a lifeless program sitting on a disk somewhere. This is a disk. And so what the OS would do first is this process called loading. Probably talked about that in 354. You load the bytes, like the program itself, instructions, and maybe some static data. And then you create, in memory, you create the address space of this program, right? So, somewhere there's code, and then a heap, which is pretty empty, and a stack, which just, the very beginning of the stack, when you're about to run, is like, what would be on the stack, actually, just as you're about to enter into a C program? Think about it. What would be on there? You're about to enter main. What's going to be on the stack? It's a mystery. Yeah. Arguments, right. You're going to say the same thing. So arguments, right? You pass in, what do you pass into main? argc and argv. So as the OS loads your program to memory, it also knows what argc and argv are going to be set to. It's going to put those in memory somewhere, and then it's going to be on on your stack. And then as you call into main, you can refer to them just like you refer to anything, right? But that's set up by the OS. So there's a little bit of stuff in here like argc and argv. And what's cool about our little OS environment that we'll be playing with for some of the projects is you'll get to see exactly how that happens. It's no more of a mystery. Some people tell me, like, what's good and bad about this class is when they're done, there's like all this magic that's gone. So we're kind of like the opposite of a magic show where we fill you with wonder. Rather, we take the wonder of stuff that you used to think, wow, that's magical, and we explain exactly how it works, and then all the magic is lost. So as I said, everything gets worse in this class, including your sense of wonder about the world of technology. So be it. Okay, so over here we have the CPU, and we're trying to just run this program, which means if we wanted to just directly execute the program, what do? We kind of set up the stack pointer to point to somewhere in the stack, and then we jump to the first instruction, which is the first entry point in main, right? Each program has an entry point. In C, the standard is its main. There might be some code that runs before there. It depends, some setup code, but we can imagine it's main. And then we just kind of go, run, program's running. And then, if that's all we wanted to do, in fact, this is kind of what early operating systems were. They were kind of this very thin shell that just lets you kind of use the mainframe in a very basic way. Like, it would let you load the program and run it. And of course, all the program was on punch cards, and it's one of those things when you hear about it now, you're like, why would people even want to use computers when they're so terrible to use? And it's actually a mystery. Nobody knows the answer to that. So fortunately, the computers have gotten a lot better. So that's direct execution, right? We just are running this program. And we've just like done a jump instruction to go to its first instruction, and then it's running. And the OS is no longer running, right? So if you think about it from a timeline perspective, the OS was running for a while, then it jumped to this program A, and then A just is running, period. And at some point, maybe A exits, and then the OS maybe can run again, because it like returns to the OS. The problem with this, in fact, there are three problems, and this is really all we're going to talk about today of these three problems, are exactly this. They are, what if A, or a process, or what we will increasingly call a user process, as opposed to the system or kernel itself or the operating system, a user process. What if A wants to do something restrictive? That we want to restrict. Like, for example, access the disk in some way, or get some more memory for itself, or even create another process itself. We might not want to let it do everything that it wants to do, because if we allow you to just do anything you want, you could immediately read everything on the disk, you could read everything in memory, and you could basically, all the secrets in the machine would be gone. You'd lose control over the machine. So what if how do we want to allow processes to do restricted things, but control it, limit it in some way? First question. So that's question one. Question two is, what if the OS wants to stop, say, A, and then run B? A is running. Let's pretend we have only one CPU because it makes our life simpler. A is running. When A is running, what's the OS doing? It's not running. When you're not running, how do you make a decision? Well, you don't. So in order for the OS to make a decision, it needs to be running, but A is running because we just jumped to A. So we need some way to kind of get control back from A so we can be the OS and maybe decide to run B. The fundamental tenet of building a scheduling policy of switching between A and B requires the OS to gain control again. So how does the OS regain control of the CPU? Third question is basically kind of an efficiency one. What if A, our process, does something that is slow? That is slow, like a disk I/O. For example, no question mark, disk I/O, exclamation point, or network I/O perhaps. So if we do something slow, we'd like to be able to, for efficiency reasons, as was pointed out very early in the class of why we might want to share things, is when somebody does something slow, they're just wasting the CPU. We'd like to switch it as well at that point. What machinery do we need to enable that sort of switching in the case of the operating system? So what we're going to do now is just answer these questions in turn. We're at 7 till 8. I think it's fruitful for us just to push through and get through this material as quickly as we can and then just be done. And then I'll stay around afterwards. Now, I keep promising to talk about the wait list for people who are on the wait list, and I keep forgetting because, I don't know, because I'm old now and I forget things more. And that's actually true. So it's quite a horrifying thing when you don't remember everything as quite as well as you used to. But I do remember that there is a thing like a wait list and that it's important to people. How many people are on the wait list? Okay, I will declare that you will all get in. So here's the way you're going to get in, okay? So there's this P.O. box where you send money. No, that's not related to that. So it's just $4,000. So anyway, how you're going to get into the course is on the class webpage. You're going to have to, first this, you have to find the webpage. On the webpage tonight, I'm going to create a link to a form. That form is going to allow you to put your name and student ID, and I will collect those and give them to the magical powers that be that enable you to enroll in this class. So you will have to find the form and enter your information into it. If you cannot remember that, then you cannot get into this class. That is the test. For the rest of you, you already got in, you're living an easy street. You don't have to fill out a form. So congratulations. But the rest of you, it looked like 10 of you or something. Now don't go tell your 50 friends because that would ruin everything. So if you're here, that's the requirement. You're here and you're trying to get into the course. It looks like we have room, right? It's not too bad. I mean, yes, it's unbearably hot. And there's no elbow room. And imagine what it's going to be like when we take an exam together. That's going to be horrible because it's going to be have you been in Ag Hall? Oh, yeah. It's squeaky. It's like 2 floors, but it seats like 600 people. And you need space. So they're going to stick us in there, I'm pretty sure. Or we'll find 2 rooms. Maybe we'll do that. But if we get it stuck in Ag Hall, we all suffer together. So don't blame me. It's not my fault we have some terrible rooms. Or maybe it is, actually. Who knows? Okay, so that's the wait list. You'll get in. It seems fine. There's not too many of you. It seems like, and probably I've convinced half of the rest of the people to drop anyway, who are just politely sitting through this process discussion. So thank you for that. Okay, so any other questions about the wait list before I just completely forget any other thing like that? So important things to remember. If you're on the wait list, go to the webpage, fill out a form, and discussion is not where discussion used to be. Discussion is tomorrow at 5 here, and we'll tape it if you can't make it. Okay, let's do these questions in order. Sorry for that off-topic thing. First, let's do, what if a process wants to do something restricted? And this will be the most complicated thing we talk about, because it requires us to have a bunch of new machinery from the hardware, as well as how the OS kind of interacts with the hardware. All of this protection machinery starts with the hardware. Like just running on the CPU, that's easy. Jump to some PC and run it. But we want to do something better. When a program wants to do a file I/O, the OS wants to get involved with that and provide that as a service and be able to check. Oh, is this user Remzi? Okay, therefore it's okay to access Remzi's file. Oh, this user isn't Remzi. It's not okay to access Remzi's file. That we have to get the OS in the way of that, and we're going to do that through a new machinery. So let's talk about that machinery right now. So problem number 1. How do we allow for kind of restricted operations in a controlled way? So we're going to, again, like I said, we're going to lean on the hardware a little bit here. And this is something people realized pretty early on when they were building systems. They realized they needed more from the hardware than just the ability to execute adds and jumps. They needed what people call the system support in the hardware that's going to help out with the OS kind of services. So people have known about operating systems forever, and they've known that the hardware people know enough that they can put support in there to help out. So we're going to start with a very simple thing. We're going to start with a mode. This is a per CPU bit. And you can think of it like that's part of like a register that's on each CPU. And what that mode is going to tell us is basically what kind of thing is executing on, what kind of program is executing on the CPU at that time. There's really 2 choices that we're going to care about. One is it's the OS, and we often call this kernel mode. That's just a historical term I'll use. The kernel, and I'll use that interchangeably with the operating system. Some people try to differentiate the 2. I don't, because what's the point? It doesn't seem very meaningful to me. So the OS, when I talk about that, and when I talk about the kernel, I'm talking about the same thing. So that when the OS is running, we're going to be in kernel mode. And when a user program is running, like we were talking about user program A, we're going to be in what we call user mode. And the good news, oh, I need to do this again. Hello. I told you it's going to be exciting 2 times, maybe 3. Okay. Yeah, see, it's already like, yeah, what's the big deal? I'm still excited by cut and paste every time I do that. What we're going to have in kernel mode is this kind of critical thing, which is the OS can do anything, more or less. This is the beauty of being inside the operating system. The OS is in control of this world, and we let it do whatever it wants. This is why, of course, it's very important that the OS, what's great about having an open source OS is it's heavily scrutinized. Imagine if the OS was, somebody like the NSA, oh, they're listening to this YouTube video. The NSA injected some code into some OS which let them look at everything in the world. That could happen. So you want to have a lot of scrutiny on an OS because it has control of the system. It can do a lot of things. OS can do anything. User programs, in contrast, can only do a limited number of things. So we're going to prevent, the hardware is physically going to prevent, it's going to prevent, not physically, I guess, it's hard to say what physical is. Hardware is going to prevent a user program, when you're in user mode, from doing certain types of things. And so that means fundamentally the hardware, the first thing we're going to give it is this knowledge. Are you running a user program right now, therefore you should restrict us, or you're running the OS right now and you should let us do whatever we want. Okay, so that's the first key concept. You have to have this bit in the hardware. Okay. So now I've told you there's a bit in the hardware. And when I say there's a bit in the hardware, I really mean like here's a CPU and there's like this little piece of memory that changes from 1 to 0. And that's all I mean. It means there's some way to change this bit from 1 to 0. We'll talk about how. And then when it changes, it's meaningful. It means you're in kernel mode or user mode. So it's a literal bit stored in a register on each CPU. If there's multiple CPUs, each one could be in user mode or kernel mode at different times. Now, what we're going to talk about then is, well, how to, get into one of these modes. And then similarly, how to transition. Clearly that transition is critical. If you can transition into OS kernel mode easily, what does that mean? That means we've lost the ability to restrict, right? That's pretty obvious. You have to be able to, a user program can't simply say, hey, I want to change this bit here on this hardware to be in kernel mode. Because if you could just do that, it would mean that you could do whatever you want. And we don't want the user programs to be able to do whatever they want. We want to restrict them so that when, and of course, why do we eventually want that? We want so when they crash, they don't affect anybody else. They can't, leak information by reading, from your memory, all those sorts of things. So the way we're going to do this is we're going to provide, first of all, we're going to do something at boot time. So logically what we're going to do is when the system starts up, it's going to boot in kernel mode. It's a fundamental trust assumption we're going to have generically is that when the system boots up, the first thing that runs is the OS, and we're going to trust the OS. If somebody can inject some other code in there, if somebody can put some code in your OS or replace your OS binary with a different thing that isn't really the OS, or it's something like the OS, but it has a bunch of code that shouldn't be running, you're going to have a problem because it's going to be running in kernel mode and it's going to have control over the machine and can do what it wants. So we're going to assume that whatever we're running is going to have our trust, and it's going to be able to manage the machine without doing weird stuff. So we're going to boot in kernel mode. Then what we're going to do is when we want to, let's say we want to run a user program, we want to be able to somehow have a special instruction that it does a couple things. It both transitions into user mode, 1, and then 2, it jumps to some particular location in the user program. So we're going to need some kind of special instruction to get from the kernel into user mode, into a user program, and change modes at the same time. It's going to change into user mode, and then suddenly you're running in this restricted mode. Similarly, and it's kind of easier to talk about it the other way first, similarly, when the user program, when it wants to do something that would be restricted, something like, let's say, disk I/O. That's a good example because it's pretty clear that why you want restrictions on what you can read from the disk. We're going to need a way to transition from user mode into the kernel and change our mode to protected mode as well. And there's one more thing we're going to need to do, but I'll talk about that in a second. So we want something that goes, it goes into kernel mode and it, jumps into the kernel. So again, this is going to be some special instruction. In fact, it's a pair of instructions that we're talking about. Now, it turns out there's one more aspect of this that we need to understand. When we jump into, normally when we jump in a program, what do we specify? What's our target? When you have a jump instruction or a branch, what are you specifying? How do you know where to jump to? Yeah. Give an address, right? You give an address that says, hey, I used to be running at main, now I'm calling a function f, or func. So func is at an instruction address and I jump to it. Excuse me for a sec. So that's all great. I give an address. But you have to be a little bit careful here. If we're going to allow a user program to jump into the kernel, saying, hey, what address do you want to jump to in the kernel isn't a good idea. Why is that? Why is that a bad idea? Why is it a terrible, terrible idea? Yeah. Yeah, if you specify an address and say jump to here in the kernel, well, if you're going to the kernel and you switch to kernel mode, suddenly you can do whatever you want, and you could jump to some piece of code that does whatever some piece of the kernel is doing. Imagine if you jump to a piece of code that's right after the part where they check, can you do this? Like there's a part of the code that says, hey, if this is okay, do it. And then afterwards it just does the thing. What if you just kind of jump around the check? It's clearly a big, it would be a big vulnerability kind of surface, you might call it, if you could just jump into the kernel anywhere. So the key thing that the OS is going to do with this mechanism that we're providing to get into the kernel and then get back out is we're not going to be able to specify an exact address. We need some way that the OS can control where you can jump to in the kernel. Otherwise, you could jump anywhere and essentially do anything. Does that make sense? That's kind of like the first, I think, hard thing that we've talked about in class so far. Hard to understand, perhaps. So we want to be able to jump into the kernel. We want to be able to change from user mode into kernel mode because we want to get some service like a file I/O. But we don't want to allow jumping to any arbitrary location in the kernel because if we did, then we could just jump to some code that does the thing we want instead of the check before there. Any questions about that? Does that kind of make sense? Who doesn't want to be talking about that at 8:07? So we need to make this a restricted jump. Maybe I'll just make that a parenthetical comment. We can't just jump anywhere into the kernel. And so the way we're going to do this whole kind of going back and forth, from the kernel to a user program and from a user program into the kernel, and with a changing of modes, is we're going to provide essentially two instructions that really come in a pair. And they are a trap instruction and a return. Oops. And a return from trap. So as we just talked about, the trap instruction is a very powerful special instruction. It's system support provided by the hardware to allow us to build OS-like features. And what it's going to allow us to do is it's going to essentially allow us to jump into the kernel, but at a very restricted that's an @ sign. Oh Christ, my writing is flailing as we go on. But at a very restricted location, and we'll talk about how that works in a second. And then we're going to elevate, our privilege, what we'll call our privilege level, from user mode to kernel mode. Okay? And then while it's doing that, of course, by the way, it's going to make sure to save enough register state so that we can return properly. Like the program was executing and then it wants to trap into the kernel. We want to make sure that we don't lose track of what was in the registers of the running program. So we have to be a little careful about that. So that's the trap. And the return from trap is essentially undoing all of those things, restoring the state of the running process, de-escalating its privilege from kernel to user mode, and then going back to right after the place where it executed this trap. Okay, so that's going to be the process. So let's think about that a little bit on a timeline. So we're running along, we're program A, we're running along, and then what we want to do something restricted. So we trap into the OS, we execute that instruction, we now inside of the OS, and the OS does some stuff for us. Then the OS, when it's done, it executes a return from trap, and now is running user A again, process A again. This again is always in user mode and is restricted, and then down here we're in kernel mode, and therefore we're not restricted. And sometimes we have a special name for these traps that are offered by the OS. We sometimes call them system calls. It's the base set of services provided by the operating system to user programs. Things like to open a file, to ask for more memory, to create another running program, to create a new process, which we'll talk about in a few weeks or near soon enough. All those things are asking the OS to do something that otherwise we're going to not let you do. And if the OS decides you can do it, it lets you do it. And otherwise it can reject you. But it's going to control that. And that's what system calls are. It's a trap into the OS and then a return from trap. And the privilege level changes. Now there's one part of that we didn't explain yet, which is how does the OS restrict where you can jump to? Because we want to be able to jump into the kernel, but not arbitrarily. And so that happens at boot time. So let's talk about at boot time again. And again, when we're talking about the boot time, we're talking about the OS starting up. And so what the OS, again, when it starts up, is it starts up in kernel mode. And then what it does is it tells the hardware where to jump to when somebody issues a particular kind of trap. Okay, so when you trap, you're going to give something like a, usually, you specify like a trap number. Like, oh, this is trap number 80 or something like that. And when the OS, when this hardware sees that trap, the OS has already told the hardware which piece of code to run inside the OS that it's okay is handling this trap. So what we're going to do here when we start the system up is we're going to, in the OS, set up all these trap handlers by issuing another kind of special instruction that tells the hardware exactly where the trap handlers are. Tell the hardware where the trap handlers reside in OS memory. See, this is what, and by the way, this is what I'm talking about when I talk about mechanism. It sounds like a lot of details, but it's important to understand those details because that's fundamentally how these abstractions are getting built. We want to give a sense of we can run user programs but limit them, which means we have to have different modes where the hardware knows about those modes. And it means that when you try to do something, like you want to get some privileged operation, for example, it means you're going to have special instructions to transition in and out of that mode and in a very controlled way so you can't just jump to arbitrary code and gain power over the machine. So that's what happens at boot time, is not only do you boot up in kernel mode, but you set up some stuff so that the hardware knows about where these trap handlers are, so that later when someone issues a trap instruction, you jump to a very specific code that the OS already knows it can handle. It does the right checks at that point to make sure that you're the right kind of process to be calling this system call, et cetera, et cetera. Any questions about that? So again, way before A ever ran in this diagram here, the OS has run and made sure that when it does this trap, it knows exactly how to do that trap. Yeah. Yeah. So there's the question is about, can we call them interrupts or traps? And it's one of these things. Computer or in any field, terminology. There's not like this body of wise people who said, here is all the terminology, and we've defined it all and made it all very clear exactly what every term should mean. So, for example, in systems, there's sometimes a confusion between traps and interrupts. When I talk about traps and interrupts, I talk about a trap as being an explicit something that's caused by an instruction. Like I want to trap into the kernel, or in some cases there's like exceptions caused by an instruction, like I try to do a floating point thing and I'm not supposed to do that thing, I get an exception. Or the instruction itself causes, and it tries to access memory, it shouldn't, there's an exception. Interrupts to me are things that happen between instructions. Like for example, after I run an instruction, the disk I/O completed and an interrupt happens, and we'll talk more about that, of course. So and now the problem is, on x86, the trap instruction is called int for interrupt. So what is that? That's just confusing. But I'll always refer to traps in that way, in the way like I'm trapping the OS, and that's a specific thing that I talk about as explicitly kind of instruction level thing that happens. And I talk about interrupts as like external events that happen between instructions, and we'll talk more about that actually a little bit today, but more later in the course. Other questions? Again, the depth of technical stuff, but we kind of have to understand these pieces. So we haven't understood one piece of this. One piece that we didn't really understand is we need to save and restore the state of the process pretty carefully. And that just means what we're talking about there is register state, really. So when A is running and it's going along, and then it traps into the OS, we have to make sure that we don't mess up its registers. You know, because the OS starts running then, right? The OS starts running, starts using registers, starts changing the PC. So somewhere in here, we have to save, say, register state before we even start really running the OS. And this is often just done by the hardware. Minimally, some of it's done by the hardware, and often a lot of it. Like in x86, as we'll see when we do one of the projects, when you trap into the kernel, all your registers get spilled to a stack, a kernel stack actually, and therefore they're all saved. And then when you're running in the kernel, you don't worry about messing up the user's program, because you don't want the user program registers to change, because that would be weird. So that saving of state has to happen, and then similarly, when we then are returning from the trap here, we need to restore the register state of the running program. And again, that's often done with some hardware assist. So to you, what it looks like when you do a trap is like your execution got halted in midstream, and then some other stuff happened, which is what you asked for to happen. And then when you return, you're just like at the instruction after that trap. It's just like returning from a procedure call, except it's a protected transfer of control, right? It's a much more sophisticated kind of procedure call into the kernel in a very restricted way. Does that kind of make sense? It takes some time. Some of these OS concepts take some time to get used to them. So today's the first blush pass over this, and we'll of course talk about this in more detail in the future. So if it doesn't all make sense, that's okay. You know, go home, let it sit in your head for a while. Maybe take a look at the book chapters too, and see if it kind of makes more sense on second viewing. Okay, other questions? Yeah. Yeah, right. So we have to make sure that when we're that question is a good question. So like, how do we make sure that the OS, when we run it, the right stuff happens too? And that's best answered. We'll do a very detailed example for one of the projects, and we'll answer all of those questions. We'll see exactly, there's this pretty interesting control flow of jumping in and out of the kernel, and only can you, in the detailed example, does a good answer make sense, I think. But that's a great question, so we'll talk about that. Okay, other questions? Yeah, the heavy material. This is kind of the heaviest material of this first part. So we've kind of answered this first question. Let's go back to the first question. Man, I am writing a lot. Pretty exciting. Now I've gone past the questions. So when a user process wants to do something restricted, we kind of had to have hardware support for that. We set up some control. We restrict things by having different modes. And then we have a way of going in and out of those modes. And that's called a trap instruction, return from trap instruction. And then we have a way to control the jump target of a trap by essentially setting up trap handlers, we call them often, inside the OS, which when we execute one of these things, we don't just jump to some arbitrary code, we jump to code that the OS says, yes, you can jump to that code. When you want to do an open system call, here's where you jump, and then the open system call runs and then returns. And that's how we keep control of the machine. So we don't have time to answer both of these questions. Amazingly, in this 3-hour lecture, we are still short of time. So you're thinking, actually, we've spent too much time here, but I'm thinking not enough. But we'll balance out by just ending on time whenever we answer this question. And then we'll do the rest later. So let's just do question 2 here, which is, what if OS wants to stop A and then run B? How does the OS regain control? So this is, again, how do we create our limited direct execution? So problem 2. Just a quick, let's get a quick sense of this and then we can stop. How to stop A that's running and then run B. Historically, operating systems have taken, and hopefully you can see the problem. Let's just make sure we understand the problem. The problem is the OS was running, and then it started running A in user mode, let's say. But then the OS isn't running on the CPU anymore. There's nothing that the OS can do when it's not running. Programs that don't run can't make decisions. It's fundamental and obvious, but it needs to be said. So A is running, and if A runs forever, let's say A is written like this. Let's say you're a really funny programmer, and you wrote this, while one, and you put a semicolon, and you're like, let's run that program. Let's see what happens. And on some early operating systems, even like Mac OS 9, for example, that would just run. And it would run, and it would run, and it would run some more. And then what would you do? Yeah, power button, right? That's a solution to all problems. If you learn nothing else in this course, it's, in the end, reboot. It turns out reboot is a very useful tool and technique in computer systems, and it's used all the time because it resets systems, it gets you back in a fresh state, et cetera, et cetera. But here, it was the only solution because the OS didn't have a way to regain control. It was something called a cooperative approach. So the cooperative approach is, I hope that A doesn't do anything bad. And bad stuff might be intentional. That's maliciousness. That's the problem of all security. Or it's just, lazy bad programming. That's a kind of a security problem, but it's just, an accidental program where people don't usually write this kind of code by accident, but it would be easy to write an infinite loop by accident, right? You just kind of get your indices wrong or something with, when you get the direction of an arrow wrong or something like that, or less than, greater than. So a cooperative approach says, I'll just run A, and eventually if A, say, traps back into the OS, then I can switch to another process, right? But if it doesn't trap, then I'm stuck. So pretty early on, even eventually every operating system design realizes that that's not a good approach. And so the non-cooperative approach is what we prefer in basically all modern operating systems. And what we might call this is a preemptive approach. We're going to preempt the running program, and we're going to forcibly force something else to give the OS a chance to run, and then the OS can then decide to run something else. So that preemptive approach is, again, based on hardware support. And the hardware support, specifically in this case, is something we call timer interrupt. So what does this mean? And I'm just quickly going to sketch this out, and then we're going to just end class because we've done so much stuff already. So at boot time, the OS runs. It's in kernel mode, as we know. We know it installs trap handlers. That's one thing it does at boot time. The other thing it does at some point before it ever runs some user code is it starts an interrupt timer. What that does, it's a little piece of hardware that says after a certain amount of time, let's say a few milliseconds, it's going to interrupt the CPU between some instructions. So while a user program's running, it's going to get interrupted, which means we stop running that program and we run the OS interrupt handler, the timer interrupt handler, and then that gives the OS control again of what's going on. So the OS is running, it sets up all this stuff, it starts running A. A is a bad process, it's malicious, it wants to run forever. But what happens is at some point, the timer interrupt goes off, and that forcibly jumps the hardware back into the OS in a timer interrupt handler. And at that point, we've regained control and we can decide to do things, like, for example, run some other process. Now, I'd like to describe that in a little more detail to you, but I'm feeling like this is a good time to end. We give you 4 extra minutes, which means you have 4 minutes of just pure joy in your life, which now you can enjoy. What are the things to remember? Discussion is 5 o'clock tomorrow here, but it'll be recorded. And if you are not registered, look for a form on the webpage. Thank you.